you're going to be able to use this equation, and let's point to what everything stands for and the unit that it uses. So the new unit on here is this delta G, and it's called Gibbs free energy, or you can think of it, it's technically change in Gibbs free energy. But we'll just usually call it Gibbs free energy. And in a way, it's a combination. It's not just simple additive, but in a way, it's a combination of enthalpy and entropy changes. Enthalpy kind of focuses on whether the reaction is endothermic or exothermic, and entropy focuses on is the reaction showing an increase in randomness or a decrease in randomness. The unit that you're going to use for this is either kilojoules or, just like before, sometimes they'll say kilojoules per mole, but kilojoules is enough. Our next part of this equation is the delta H. This is something we've seen a lot. That's just your change in enthalpy for a reaction. And we know that its unit is also kilojoules per mole, because we calculated that a lot in our last chapter. Next, we've got a capital T. Capital T must be a Kelvin temperature. So this equation only works with Kelvin temperatures. If they give you Celsius temperatures, you got to change it, because all of this thermodynamic stuff is based on these laws of thermodynamics, the third of which is that absolute zero is where you have zero entropy. So here we have our Kelvin temperature. T stands for temperature, and it must be Kelvin. All right, and then finally, our last little part here, I'm going to put parentheses around it to kind of separate it. You'll multiply that Kelvin temperature times the change in entropy. So that's my last part of this equation. I don't want to cover that up. It's important. So this last one's going to be change in entropy. And before you calculate with it, you need to make sure that it is also in kilojoules. And the unit for it is kilojoules per mole. Then after that, you're going to see Kelvin. And what that means is, so those entropy values, when you look them up on this table, in Appendix C, if you had looked at any of these, all these delta S values, they say joules per mole Kelvin at first. So before you calculate with them, you need to move that decimal 3 places over so that it's in kilojoules. So if I look up a delta S on this equation, or if I'm given a delta S, they're usually in joules. So for one of these, it's 175. Before I calculate with it, I need to call that 0.175, because you can only add kilojoules to other kilojoules. You don't want to mix kilojoules and joules in the same equation. So it's just a little tricky thing to watch out for. Before you calculate with delta S, be sure you're in kilojoules and not joules. And the fact that it's kilojoules per mole Kelvin means that it's temperature dependent, and that's why we're multiplying it times the temperature as shown there with the capital T. All right, so then you calculate your delta G, and what you're most interested in is whether it's positive or negative. This is something we saw before when we were dealing with endothermic and exothermic. Well, with delta G, we're also interested in whether we have a positive or negative delta G. Two halves to that equation. Again, this is what delta G puts these two things together. The delta H term is what we call the enthalpy term. So the enthalpy term is where we're going to decide, okay, is it positive and endothermic, or is it negative, which is exothermic? And then the T delta S all together, we call that the entropy term. So sometimes you're going to be looking at the equation and the numbers that you end up plugging into it, And you have to decide, is the enthalpy term helping to drive that reaction forward? Or is the entropy term driving that reaction forward? So we want to be able to identify the terms that we use for those two halves of the equation. This next slide is on your sheet. This is the most important thing to know about Gibbs free energy. We want to be able to use the equation and talk about the equation, but this is the most important thing, is your answer when you solve for delta G. When you get a delta G, if it is negative, that means the forward reaction is favored. That's what we mean when we say spontaneous. I'm going to write the word spontaneous beside of that one. And people always say, well, wouldn't it make sense if positive meant it's favored? Don't we think of positive being more forward and favored? Well, again, it has to do with the idea that this is all about that second law of thermodynamics, which says that for something to happen spontaneously, energy and matter must spread out. Randomness always wins. Either the system or the surroundings itself, or maybe both, will become more random in nature. When delta G is negative, it means that in some way energy or matter are leaving kind of the consolidated system and they're spreading out from the system to the surroundings overall. And that's what the second law of thermodynamics is about. If delta G is 0, that's very rare. That almost never happens. But if delta G were 0 exactly, the system would be at equilibrium, meaning the reaction might be going forward and backwards at the same time and even at the same rate. And then finally, if you solve for delta G and it's positive, that would mean the reaction is not favored. So the reverse of the reaction is favored. So an example of something that would have a positive delta G would be like the reaction for when you charge your battery in your phone. So you have to plug in your phone to charge it because that requires energy input. That phone's not going to charge itself just by sitting there. So if you had the numbers that went with the reaction for the charging of a battery in your cell phone or something, it would give us a positive delta G. There's other examples too that we're going to look at and see. So this gets back into focusing on the equation again. So the most important thing is really just the sign of your delta G. But what is it that influences the sign of that delta G? These are the two factors we're going to be looking at. Either a decrease in enthalpy, which means exothermic, and an increase in entropy having a positive delta S. Mathematically, these are the things that would help you solve this equation and get a negative answer. Chemical and physical processes are driven by a negative delta H, which is a decrease in enthalpy of the system, and an increase in entropy, positive delta S. If you think about positive and negative numbers being added and subtracted, this makes sense mathematically. If you've got some numbers and you're going to solve for delta G, if you take a negative delta H, so maybe it's negative 5 or maybe it's negative 5,000, just negative something, minus, okay, your Kelvin temperature, is there such thing as a negative Kelvin temperature? No, Kelvin temperatures can't go negative. So T is not going to affect your sign. And then your delta S is a positive number. Just in math, anytime you take a negative number and you subtract a positive number from it, you have no choice but to get a negative answer for your delta G. That is why reactions that have a negative, that's why I always mathematically with the formula, reactions that have a negative delta H, which is exothermic, and a positive delta S, those reactions always happen spontaneously. That's what the second law of thermodynamics is about. If a reaction is exothermic, that means energy is spreading out. That makes the universe more random. And if it has a positive delta S, that means maybe that reaction increases the number of moles of gas particles, or maybe the molecule becomes less complex. In some way, having a positive delta S means the system itself is also becoming more random. And if it's got a negative delta H, that means it's heating up the surroundings, so the surroundings become more random. So those kind of reactions always happen spontaneously because they follow that second law of thermodynamics. So we're going to start thinking about, what about other signs? What if it's exothermic but it has a negative delta S? Or what if it's endothermic and it has a negative delta S? How do all of those things work out? So that's something we're going to think about actually in just a minute. First, I just wanted to practice with the equation. And so this is at the bottom of the handout that I gave you. Let's practice with that equation with some actual numbers and think about what the sign of the delta G means and how that relates to whether the reaction is spontaneous or not, or we could say it's favored or not. So this question says, a certain reaction has a delta H of negative 19.5 kilojoules. Sometimes that will say kilojoules per mole. And a delta S of 42.7 joules per Kelvin. That's in joules, so before I work with that one, as soon as I notice it's in joules, I'm going to move that decimal 1, 2, 3 places and call it 0.0427, and then I can call it kilojoules per mole, Kelvin. Okay, first of all, A just says, is the reaction endothermic or exothermic? Well, just look at the sign of your delta H. That's all you got to do for this first question. I notice my delta H is negative. So Alice, if you have a negative delta H, is that endo or exothermic? Exothermic, you got it. I'm just going to put a little reason here because I have a negative delta H in the question. Does the reaction lead to an increase or decrease in randomness? Mackenzie, just based on those numbers they gave us, would you say it's an increase or a decrease in randomness? Increase, yeah. Positive is increase. Positive delta S. BC means because. It's just my shorthand. Because positive delta S. Increase in randomness there. Now let's get into the new stuff here. Calculate the delta G. All right. Delta G equals delta H minus Kelvin temperature times the delta S in kilojoules, negative 19.5 minus, it gives us a temperature even. It says use 298. That's what we call standard temperature. It's 25 degrees Celsius, which is room temperature. All right, times 0.0427 kilojoules per mole Kelvin. I just left out the mole part. So before I even touch my calculator, I just want to focus a little bit on the signs just to know for sure. Sometimes you can know. For reactions that are exothermic and have an increase in entropy like this one, I can look at these signs and I know there's no choice but for me to get a negative number here. If I take a negative number and then I subtract a positive number from it, the value goes down on the number line, right? So we started negative. We know we're becoming more negative. I know it's a negative delta G. So I actually know the answer for part D. If part D just wants to know is it spontaneous or not, I know for sure this one's spontaneous before I even calculate my actual delta G value, because it's exothermic and it has a positive delta S. But if I actually want to find it here, I'll just multiply and then just do the subtraction. All right, I'm going to go with 3 sig figs, I think, and I'm going to say negative 32.2 kilojoules is enough. Sometimes you might say kilojoules per mole. The little per mole part is kind of supplemental. It's really there, but they don't always put it in the question. The value of it lets me know, if I wanted to compare it to another reaction, I could compare it, but more than anything, I care about the sign. And the sign helps me answer question D, which I already knew, but it is spontaneous. And the word we're going to use a lot for spontaneous, they started using a new word for it a few years ago called thermodynamically favored. I'm just going to say thermofavored. This reaction is favored to happen on its own without outside intervention. Maybe it takes place over 1 second, or maybe it takes place over a century. That's why we stopped using spontaneous, so we don't have to think of it as fast anymore. It just takes place on its own. No matter what, guys, if a reaction is exothermic and has a positive delta S, it's going to be thermodynamically favored because energy is spreading out and matter is spreading out and becoming more random in some way. So when we focus back on that on the equation itself, the delta G equation, it had the two halves to it. We talked about the enthalpy half, the delta H, and the entropy half, which was the delta S. If I want to know, is this reaction driven by enthalpy or is it driven by entropy, or possibly both, again, you just have to look at the signs. The last example we looked at had a negative delta H and a positive delta S. It was favored no matter what the conditions were because it was both enthalpy driven and entropy driven. If it's got a negative delta H, like that last example did, that helps you get a negative delta G by having a negative delta H. That also means that energy is spreading out. That's what the second law is all about. Matter and energy want to spread out in the universe. So the negative delta H reminds us that energy is spreading out. That drives the reaction forward. And if a reaction happens to have a positive delta S, that means entropy is also driving the reaction forward because matter is spreading out and becoming more random. Yes, sir. What if they're signs? What if they're both positive or if they're both negative? Great question. That's what we're going to talk about in a minute. Then they become temperature dependent. So a reaction like the one we're seeing here, if it's a negative delta H and a positive delta S, it means no matter what the temperature is, and you can think of this with the formula too, no matter what you plug in for T, for your Kelvin temperature, those always have to have a negative delta G. When the signs match, that means those are temperature dependent. There are certain temperatures below which they are either favored or not favored, or temperatures above which they are favored or not favored. And it has to do with whether the signs are both positive or whether the signs are both negative. And that's a great question, and that's actually kind of something that's coming up. When the signs are opposite for delta H and delta S, they're either always favored like this, or if it's a positive delta H and a negative delta S, they could be never favored. But it's when the signs are the same when we have to start thinking about temperature. So here it is. This is perfect timing there. When enthalpy and entropy are opposing each other. So for instance, when you have negative signs, if a reaction is exothermic, hey, that's a good thing for a reaction. Exothermic reactions are likely to happen because they spread out energy. But if the delta S is negative because the system's particles were becoming more ordered and less random, we got a problem. Sometimes the reaction is favored and sometimes it's not. It depends on the temperature. And in a minute, we can actually find specifically that temperature for certain reactions. Exothermic processes are favored at relatively lower temperatures when you have an exothermic reaction, but it leads to a decrease in entropy. And I always like to focus on this word relatively lower, because sometimes people see that and they think it must be low compared to the weather or compared to how I feel. but we're talking about some specific temperature for every reaction where it switches from favored to unfavored, at least for these reactions of having the same signs. If a reaction or a process has a positive delta H, so it's endothermic, but it also leads to an increase in randomness, that would be a reaction that's more entropy driven, and that one is also going to be temperature dependent. When the signs are the same, they are temperature dependent. When they're both positive, like we see in the second bullet point here, these are favored at relatively higher temperatures. So there's some temperature at which the reaction switches from being less or not favored to suddenly becoming favored. All right, so this chart, I'm gonna recopy maybe this chart where it's a little simpler, but I just want to show you some possibilities, and then don't copy this one down. We'll make our own summarized chart because there's extra stuff on here we don't have to have. When the signs are opposite, let's just look at the first one. When delta H is negative and delta S is positive, those are two things that always drive reactions forward: exothermic and increasing entropy. Those are spontaneous or favored at all temperatures. When the signs are the opposite here, you have a positive delta H and a negative delta S. Oh, a positive delta H means energy is coming into the system to make it endothermic. And it also has a negative delta S. That means the system itself became less random. That's not good for reactions. Neither one of those is good for reactions to move forward. So those would be non-spontaneous at all temperatures. They become more interesting when your delta H and delta S have the same sign. When they're both negative, they're spontaneous at lower temperatures. Lower than what? It just depends on the reaction. And when the signs are the same here, if they're both positive, those are spontaneous at relatively higher temperatures. So let's summarize that. Maybe also have maybe an example reaction just on your paper. So we're going to kind of make a table that summarizes all of that together. So we're going to have the delta H column just like they did. We're going to have a delta S column. And then let's just go straight to delta G because that T delta S part kind of makes it more complicated. And then we'll say how they're favored and when. We'll say favored and we'll say yes or no. Instead of the word spontaneous, we'll use that word favored now. And then let's also think about an example for those. Sometimes having an example helps me remember why some things are favored or not favored. All right, so the first option is my favorite, exothermic and increase in entropy. Just put a little up to remind myself that means increase in entropy. That always has a negative delta G, no matter what the temperature is. So favored, yes. An example of that would be any kind of combustion reaction would be one of those. I'm going to use one from your biology class, photosynthesis. The other one, respiration. All right, so this, you go from, even when this is balanced, like you balanced it in your biology class before, this 6. Just to kind of review from yesterday, or from 2 days ago, something like that. we definitely know that any kind of combustion, even if it's respiration, that releases energy for sure. And then also you can count your moles of gases, just to see you go from 6 moles of gases to 12 moles of gases. Definitely an increase in the entropy there. All right, next example, let's go with the other way you could do the signs being opposite. So if you have a reaction that has a endothermic positive delta H, decrease in your entropy, oh, there's no choice mathematically but to get a positive delta G there. So those are never favored. And so an example of that would be the opposite here. I almost put this one on the last one. Photosynthesis. Photosynthesis happens, but does it require energy input for the plant? Yeah, it requires the sunlight for energy input. So that just helps me kind of remember the idea here. This reaction is becoming less random, and I know photosynthesis requires energy input. So it's endothermic in that way. All right, now back to the signs being the same. If they're both positive, if it's endothermic, but it does lead to an increase in the entropy, at least, of the system itself, those are going to be negative at higher temperatures and positive at lower temperatures. So we could say yes at high T, and say no at lower T, lower temperature. And that means that that magical temperature depends on the particular reaction. And we're going to practice solving for temperature on the next slide. So can you think of an event that happens on its own at relatively higher temperatures, but not something that's spontaneous at some temperatures but not others? This was from that reading. So it was, think about ice melting, right? Ice melts at higher temperatures but not lower temperatures, right? So for ice to melt, that's an endothermic event, but the particles themselves start speeding up and moving around more, so it's a positive delta S. And so we'll have the pattern being the opposite order on the last one here. We're going to have negative signs for both of those. These are not favored at higher temperatures. They are favored at lower temperatures. So these exothermic reactions that have a negative delta S, they are favored at lower temperatures. So we say no at high T, T for temp, and yes at low temperature. So the opposite would be here, water freezing. Water freezing is actually exothermic, and the particles lose some of their randomness, and that means the signs match. They're both negative signs there for the H and the S. And if you ever get mixed up on those or lost on them, you can always plug in, put the signs in that delta G equation. It can always go back to that delta G equation to see why you get your delta G signs the way they appear there. All right, so that chart's going to be important for us to know those relative differences. Does anybody need more time on the chart? Okay. So last thing I want to do is look at a reaction where you have matching signs and practice finding that temperature and decide, okay, compared to this temperature, is that higher or lower temperatures that it's spontaneous, and what is the particular temperature itself? So this is, I think it might be on that page also. We're looking at this reaction. Let me take the little thing off the top of the page here. There we go. So looking at this reaction, 2POCl3 yields 2PCl3 plus O2. I can look at this reaction and know it has a positive delta S even before I look at the numbers. How do I know for sure this reaction has a positive delta S? Before I even read the paragraph. Yeah. You got it. There's more moles of gas on the right-hand side. I see 3 moles of gas on the right-hand side. So before they even tell me the delta S is positive, I know it. But they even give me the number. It's 179 joules per Kelvin. All right, I want to go ahead and move that decimal so I got it in kilojoules. I don't know why, but entropy is always in joules at first, but before you calculate with it, you need to put it in kilojoules. The value for delta H is positive 542. Oh, they're both positive. When they're both positive, I know those are the temperature-dependent reactions. We can use those numbers to actually find the temperature at which this becomes spontaneous. So let's actually solve for T instead of just saying to solve for T here. So if I want to put the numbers in, solve it for T, I'm in kilojoules. I'm going to get my answer in Kelvin because the standard unit here is Kelvin. I'll go ahead, I'll subtract 542 from both sides. I'll get negative 542 equals negative T times 0.179. Let's divide both sides by 0.179. And then we'll get rid of that negative sign on both sides after that. So I'm first getting, I'm negative 3028 equals negative T. So I can take that, I would do this one line below there. I'll say T equals about 3030 Kelvin. All right, that's the temperature, but I want to focus on what the answer means. The answer isn't just this idea, 330 Kelvin. I want to think about what it means. That means for this reaction, there's a temperature at which it switches from favored to non-favored. Let's go back to the chart we just wrote to think about. Both of those signs for the S and the H, they were both positive. So if they're both positive, is this reaction favored at temperatures above 3030 Kelvin, or do you think it's favored at temperatures below 3030 Kelvin? Pavitra, when they're both positive, do we want to go with the higher or the lower temperatures? When they're both positive, actually, we're going to go with higher temperatures. So for this one, and if you aren't sure of it yet, you can look at the chart we just wrote. If you go to the chart we just put down, when you see that both were positive, the delta H is positive and the delta S is positive. If you go over to the right-hand side, we put down that it's favored at relatively higher temperatures. So this reaction, I'm just going to put this here, I'll put this reaction is favored at temps higher than 3030 Kelvin. So we set it equal to 0 and solved for temperature, because when delta G is 0, that's when it's switching from positive to negative. That is why to find that temperature, you know, they never told me what I should plug in for delta G. They just said solve for T. But I set my delta G equal to 0 because that's the delta G at which it switches, that's any number, switches from positive to negative or negative to positive at 0. So that's going to lead to the temperature at which this switches from favored to not favored. When both signs are positive, it's favored at temperatures above that mystery temperature. When both delta S and delta H are negative, we would have said the reaction is favored at temps lower than 3030 Kelvin. Because when they're both negative, those are favored at relatively lower temperatures. Relative to what? To whatever you get when you solve for T using this equation. Not relative to what feels hot or cold to the human being. Okay, guys, I know that was quite a bit. There's one more thing I just want to go over, but the last thing is something we've done already twice before in this class, if I can get this to change. One more thing you can do with this set, something we've already done with delta H's, we've already done it with delta S's. The last thing we can do the same exact thing with the delta G column. So this also had a delta G column. You can use it to do products minus reactants again. And one thing, just like delta H, delta G will also have 0 values for for elements in their natural state. So like aluminum is naturally a solid. So for solid aluminum, remember that delta H of formation was 0 because that's aluminum in its natural state. S didn't do that for us. S always has a value because everything has some entropy as long as it's not an absolute 0. But delta G also is 0, the same places where the delta H of formations were 0. So for pure elements in their natural state, you can assume that the delta G of formation is 0, just like with those delta H's. So this is the last thing we got to do, but it's something you've done before. When you're given the delta G of formation, or if you've got this Appendix C paper handy, you can do the same thing we've done with our delta H's, and you can find a delta G for a reaction just by subtracting the products minus reactants. So the delta G for a reaction can be found by doing the delta G of the products, keep up with those coefficients, minus the delta G of reactants. So for this equation, we'll say 2 times SO3, we'll look it up on our table, minus the sum of 2 times SO2. Oh, did it do that again? I got to refresh. Let me just do it on the board. Showing up on the wrong screen for some reason. There we go. Let's do our delta G of products minus reactants. Delta G of the products minus the delta G of the reactants. And the little f just means these are formation values. We'll say 2 times SO3 minus the sum of 2 times SO2 plus 1 oxygen. But just like with delta H of formation, I know oxygen gas is going to be 0. That'll make the math a little easier. All right. 2 times SO3, they just gave it to me, so I don't even have to look it up here. Negative 370.4. Minus 2 times the SO2s are negative 300. All right, and then I know that last part's plus 0. All right, the first part's negative 740.8. Minus a negative 600.8 plus a positive. All right, I'm getting negative 140. I can say kilojoules or kilojoules per mole. Let's think about what that means, though. If I have a negative delta G, is this reaction, can I go ahead and know that this reaction is favored or not favored? Joseph, is this reaction favored or not favored? Favored. Yeah, so this reaction is favored. They didn't ask me to find that, but, oh yeah, they did. Up there. Yes, it's favored because it's a negative delta G. All right, so two different ways to find delta G. Most of the time we'll find it with delta G equals delta H minus T delta S, because that's where we're really focused on the two concepts we've studied, enthalpy and entropy. But for standard conditions, if you have the formation values, you can always fall back on the same thing, products minus reactants, to show that. So for the last little bit, I'm going to have you work on this homework that kind of reviews all of this stuff. The one that I want to do together as our first one, though, is going to be 4A, just to focus on the idea of whether a reaction is enthalpy-driven, entropy-driven, both, or neither. We talked about that quite a bit, but there's always a question once you actually have to do it yourself and focus on those two ideas. So I want us to take a look at number 4A together first. It's two sheets that just didn't staple for some reason. About number 4, but never saw it with numbers. It's actually really easy once you know what to do here. So it says, given the following thermodynamic values, determine how temperature affects the spontaneity of the reaction. And to do that, we're going to decide whether it is enthalpy-driven, entropy-driven, both, or neither. All right, so this first one, it's got a positive, it says delta H is positive 327 kilojoules. Delta S is positive 127. You don't have to do any math here, you just have to look at signs. All right, so remember, enthalpy drives a reaction when the reaction is exothermic. Entropy drives a reaction when it increases in entropy. All right, well, looking at A, is A considered to be endothermic or exothermic? Piper? No, don't worry about temperatures yet. I know the question mentions that, so you want to go straight to that. Let's just first focus on the delta H being positive. If delta H is positive, is it endothermic or exothermic? Endothermic, you got it. I'm even going to write that on top. I'll just put endo on top of it just so I remember that. All right, and then my delta S is positive 127. So that leads to an increase in entropy. All right, reactions are favored by being exothermic and having an increase in entropy. Well, this one only is favored by this part of the two halves. So this reaction we would say is entropy driven because it had a positive delta S. This reaction is not enthalpy driven because it has a positive delta H. A reaction is only enthalpy driven if it has a negative delta H, because that means it's exothermic, so energy would be spreading out and that would have driven it forward. In this case, energy is coming into the system, so the energy doesn't get to spread out, it actually does the opposite. So this one's entropy driven. And just to practice with the temperature situation, because it's good to practice with that chart. We've got it on a chart, but we need to know this. If both signs are positive, are those typically favored at relatively higher? And this is what you were trying to jump to, Piper. If both signs are positive, is this one more favored at relatively higher or relatively lower, or all or no temperatures? Shelby, what happens when both signs are positive in terms of temperature favorability? Yeah, so we'll just put a note here. There's not a great space for that, but I'm just going to put it right after the question part of it. So I'm just going to put favored at higher temps, just to practice with that. It's not really part of the question. But I want to make sure I can find on that chart whether a reaction is favored at higher temps, lower temps, no temperatures, or all temperatures always. So use the signs of your delta H and your delta S to decide if it's enthalpy driven, negative delta H's, if it's entropy driven from positive delta S's, or both or neither, depending on those opposite signs.